Hi, today we are going to learn about Michaelis and Menten equation. I will be not deriving this equation in this lecture. You can go and check YouTube videos for that. You have plenty of videos where the people are deriving Michaelis and Menten equation. Today I am not going to derive this. I am explain this equation in context of biopharmaceutics, that too in absorption. So we'll try to see what this Michaelis and Menten equation explain about active absorption. If any drug is undergoing active absorption, how can we explain that absorption pattern by taking Michaelis-Menten equation? So we'll move on to the equation now. So I'll just write the equation. The equation says velocity is equal to maximum velocity into concentration divided by Michaelis-Menten constant plus concentration. So this is the equation which is been derived previously. Okay, I am not going to derive this equation. I will be explaining what is the context in terms of absorption. So in this check this graph. In this graph we have three parts. Okay, first part is, take this as a linear line, then curve, and this is okay. So we have first part here, this one, second part here, this one. So this is the first part, this is the second part, and remaining is third part. So this graph has three parts here. I will try to draw this here, check here, yeah, take velocity, so it will be like this. So I will be drawing the graph like this. Okay, it has three parts. Now we will try to see case 1, case 2 and case 3, what happens in case of absorption, in case of active absorption. Okay, absorption through carrier mediated system. So case 1, yeah, let's say case 1, what is happening here is, case 1 we can take it as like Km is much greater than concentration. So your Km is much greater than the concentration. In such case, what happens to the equation? So equation, I will just write the equation. Because your Km is much greater than the concentration, we can neglect this concentration. Km plus C will become Km. Hence we can rewrite the equation as, Vm C by Km. So this both are constant, maximum velocity and also your Michaelis-Menten is also a constant. So I can write it as velocity is equal to constant into C. What do you mean by velocity? Change in concentration by change in time is equal to Kc. Now check this equation. How this equation is what this equation is representing? It is representing first order. Okay, so rate of reaction is directly proportional to the concentration. That's what this equation is representing. So I'll try to draw the graph for this equation. In the Michaelis-Menten equation, the first part is represented by this equation. First part in the sense, check here, I told you this part. So this first part is represented by your case 1. Okay, this one. So this part is been represented by, I'll draw here, okay, yeah. So this part, the first part is been represented by your first case. So what it's saying is, yeah, see here, what it says, I will try to draw the full graph here to avoid the confusion. Okay, something, this graph will look like this something. Now this equation represents the first part of the Michaelis-Menten graph. This part, what it says, velocity is increasing over the time, means as concentration increases, the velocity is also increases. So what is happening here? As the concentration of the drug increases, the absorption rate of the drug is also increases. What do you mean by this is, assume that you have a membrane and assume that this is a GIT, you have a membrane here. Okay, in this membrane we have active carrier mediated system. Let us say in this membrane we have carrier mediated system. Okay, like this, in this membrane we have carrier mediated system. Let us say this carrier mediated systems are 50 in number. Assume, just one thought experiment we will try to do here. We have that these carrier mediated systems are 50 in number. Slowly I will increase the drug concentration within the GIT. So here it is blood and this is GIT, inside GIT. Okay, slowly I will increase the drug concentration. If I give 10 molecules of drugs here, okay, check this, if I give 10 molecules of drugs here, because the carriers are 50 in number, all the molecules are being absorbed. Then if I increase further 20, again all the molecules are absorbed. If I increase the concentration to 30, all the molecules will absorb, because the carrier system here is 50. Okay, all the molecules will get absorbed as the concentration is increased. So that what this equation is represent. Case 1, if Km is much more than concentration, in that case that Michaelis-Menten equation is being modified like this, and it is showing it is being modified in the form of first order reaction. And also there is a straight line we can see here. So this line is explained by this particular equation. So what is happening? As the concentration increases, absorption rate also increases. So it is directly proportional to the concentration, hence we call it as a first order. That what is explained in first part. First order kinetics. Okay, next we will try to see the case 2. Second case, your Km as well as concentration both are significant. Okay, both are significant, you can't ignore both. In such case what happens, your equation will remain as such. Because both are important, your equation will remain as such. So what does it indicates is, neither the velocity is dependent on the concentration nor the velocity is not dependent on the concentration. It is showing mixed order. Previously it is showing first order, now it is showing mixed order. It is both, neither it is dependent nor it is not dependent, both zero order or first order. So this part is being explained in the graph of the Michaelis-Menten equation here. So this particular part is explained by this equation. So when Km and C, constant and as well as concentration, are significant, you can't ignore both the terms. In such case what happens, this particular equation remains as such, and it explains the velocity neither dependent on the concentration nor it is independent on the concentration. It is showing mixed order. So what is happening here? That what this equation is saying. Okay, now we will see what is happening here is, again we will take a GIT here and we have blood and we have some actively absorbing species. Okay, so if I increase the drug carrier mediated system, how many I have? 50 molecules of carrier mediated system in number, 50 in number, they are present in the, assume in the GIT. Okay, so now in the first case we increase the drug concentration till 30 or 40 like that. Okay, now when the concentration reaches to 50, then beyond that 55, 56, okay, or you can say till 60 or 70, what is happening here? The 50 molecules, see here the drug molecules is 50 and all the 50 molecules will go and attach to the carrier mediated system because they are also in 15 number, and all the drug is been absorbed. So initially it is first order, all how many molecules are there, that much molecules are absorbed. If I further increase the concentration to 55, what happens here? Few molecules will go there, okay, and your actively absorbing species, that is your carrier mediated system, it will take few molecules of carrier mediated system after leaving the drug in the blood, they will come back and again pick up the molecules which are present in the GIT. So it will be a slow process, only few will come back, okay. So slowly there will be a limiting which is going to occur. Hence we can clearly see here the shift is both, it is initially dependent, that is first order, and as the concentration increases from 55, 60, 70, it will shift to zero order. Means in this case, when the concentration and the constant are significant, or you can say the concentration is in medium level, then what happens? Medium in the sense what? Compared to the concentration of your actively absorbing species or carrier mediated system. So here concentration is slightly more than the carrier mediated system. In such case we can absorb both first order as well as second order, that we call it as mixed order. Okay, we call it as a mixed order. That what happens in the case 2. So slowly there is a shift, hence we get a curve there in the Michaelis-Menten graph. Now the third case is, case number 3 is, if concentration is much more than Km, what happens? Initially concentration is less than Km, then we have concentration and Km are both significant. In the last case we have concentration is much more than Km, means higher molecules of drugs are there in GIT. So we will see first in the equation C by Km plus C. So I said concentration is much more, hence Kmc can be written as C, Km plus C, because Km is very less, we can take this Km plus C as C. So if you modify the equation, velocity is equal to Vm C by C, again this C will get cancelled. So velocity is equal to Vm. What is Vm? It is a constant. Maximum velocity is a constant term, means what? Velocity is dependent on nothing here, means it is zero order. Zero order means what? If you keep on increase the concentration of drug, there is no significant change in the drug absorption. Even though increase the concentration of the drug, there is no significant change in the drug absorption, because here the saturation of your carrier mediated system is going to occur. I will tell you in this example. Let us say we have GIT, lining, then blood here, and we have carrier mediated system that are, we assume that are 50 in number. Okay, if I increase the drug concentration to 100, or let us say 200 molecules. Initially we start with the 10-20 and we now reach to 200 because concentration of drug is much more. What happens? Within this 250 molecules will go and join, will form a bond with your carrier mediated system, and it is been carried through a 50. So 50 molecule will absorb. Now I will increase the concentration to 300. Then also only 50 molecules will go bind and again 50 molecule absorb. Now again I will increase the concentration to 400. Then also the rate of absorption is 50 molecules only. So what is happening here? Only 50 molecules are absorbing even though I am increasing the concentration. So it indicates zero order. This can be represented in the equation like this. So whatever the plateau you are seeing, the velocity is not changing over the time even though there is increase in the concentration, because concentration is more, your carrier mediated system is getting saturated. Whatever the carriers we have, only 15 number we have there, it is getting saturated. The number 50, what I am saying is just for your imagination. Okay, we are making a thought experiment here. So this how we need to understand the Michaelis-Menten equation in terms of biopharmaceutics, or you can say active absorption. Okay, mixed order kinetics. We call it as a mixed order kinetics because while the drug is undergoing active absorption, in such case your passive diffusion, or you can say linear kinetics, is not observed. Okay, because in passive diffusion either the rate of absorption is dependent on the concentration or independent on the drug concentration, but in case of your active diffusion, active absorption, your rate of absorption is dependence and independence will be keep on changing. Initially it will be dependent, then it will turn to mixed, and then it will become independent. Okay, as you increase the drug concentration, that what the rate of absorption will be keep on changing its dependency. Hence we call it as a mixed order or non-linear pharmacokinetics because it involves active carriers. Now this particular thing I explained about absorption, you can apply this to excretion also, you can apply this to metabolism also, you can apply this to protein binding also, distribution also. Wherever there is an involvement of enzyme is there, or protein is there, or wherever there is a formation of drug protein complex is going to occur, in such case you can apply this Michaelis-Menten equation in ADME also. Okay, I explained about only absorption, you can apply this to distribution, metabolism and elimination also. So that's how we need to understand this. Okay, I hope you understood.